This is the first lecture that really applies to the famous fields of physics. The Coulomb and the oscillator are the, anyone who's taken quantum mechanics knows that's the ones you study midway through the course. And it's the fields that apply to atomic physics, a little bit to nuclear physics, and certainly to quantum optics and to quantum mechanics in general. So certainly the oscillator is the most important of them all in terms of just general ideas. I want to show you the geometry of them, geometry of any power law potential, just a little bit of the idea of geometric series. Why is it called a geometric series? It's a power series. The zigzag construction that we used a little bit of last time to get fractions, we will get a geometrical exponential, actually, function out of just that construction. This is not widely known. I haven't seen it in any other book that uses geometry for physical purposes. The idea of perspective is very important to the history of design of buildings and also to art. When artists discovered perspective, there was a renaissance going on. The parabolic geometry of the harmonic oscillator, I think you'll be amused by it and have more respect for the potential that makes the oscillator. These are, of course, the linear force fields that we talked about last time. It's the force for a balloon. And then the Coulomb geometry, that's what I'd like to plot on the board. And while we're doing, or before we do it, we'll compare the Coulomb geometry of electrostatics with that of gravity in terms of just the size of things to get an idea of how big things are. And then this thing I call the sophomore physics Earth. It has a Coulomb field outside and an isotropic harmonic oscillator field inside. The contact geometry, which we'll introduce today, of the potential curve, namely the parabola, is very important. So that's where this geometry will come in there. Then I want to have a little lecture on something that's about the size of your fingertip. I've got a number of things here that I want you to look at. How much charge do you have in a fingertip? What kind of energy is associated with that little pinky? What would happen if you had something that was that size that was made out of nuclear matter? It is a neutron star. I call this the neutron starlet. The neutron starlet will be the main character of the next lecture as we consider orbits inside the sophomore physics Earth. So we'll have this wonderful fiction of a thing about this big tearing through the Earth, but of course to the neutron starlet, which is so dense, so massive, the little bit of rock and iron that it runs into is cotton candy. It just continues and doesn't orbit it as though it was in a vacuum. So we'll study those orbits because they are what lead us back to our Lagrangian and Hamiltonian mechanics of ellipse. The idea is that inside and outside the Earth, the orbits are conic sections, and for what we'll be doing, they're both ellipses. So that makes for some interesting things. Then I will go to the ultimate limit. I will ask you how big would the Earth be if you crushed it down to the point where it reaches a Schwarzschild singularity, and we'll describe what that is. Then we'll come back and begin to describe the orbits that you get inside with a harmonic oscillator. A three-dimensional harmonic oscillator is, in fact, what the potential is. So let's look at the zigzag exponential geometry. here's how you would want to make a geometric series, a power sequence. Say you wanted to take a number, S, here I've taken 1.5, which is right here. S to the first power is 1.5. Then you ask, okay, what would be S squared? How do you get that geometrically? And the answer is you simply go to the 45-degree line, the y equal x line, and then bounce off it and come up to that point. And that will be S squared. Then if you want S cubed, you keep going. Go across to the y equal x line, and then bounce up. There's your S cubed. And go the other way too. You want S to the minus 1 to plus 1, which is S to the 0. Come down to here and bounce. Well, S0 is 1.0, so no problem there. But if you want S to the minus 1, come down to the 45-degree, bounce, and so forth. So that's where a geometric series, the name geometric series comes from, I think. I haven't read anywhere that this is the case. We've all used the terminology geometric series. That's the easiest way I can think of to get one. Pick your S anywhere and make the staircase, the zigzag staircase. We're going to use this construction down in this region to make the Coulomb potential over here, and we'll make some parabolas that way too. But let me show you, let's just extend this a little bit. Once you've done this, if you're willing to draw a little dot right on whichever exponent you're talking about, okay? Like 3 you draw there, and then 4 you draw there, and then as you come down here to 1, you draw it right over the 1. And then, if you wanted to go with the fractions, you see, you'd go back, and this is minus 1, so you'd extend this dot out to the minus 1. And then when you came to minus 2, you'd extend the dot out to minus 2, and so forth. You see a shape to those dots? Your eye should spot that. You've just drawn the integral parts of an exponential function. Isn't that cool? And while you're at it, you can do the reverse, the inverse function. This is y equal s to the x. This is x equal s to the y. Or y equal the logarithm of x. So there's the logarithmic function, to the degree. Now you want to pick numbers that are a little closer to 1. You'll get more dots. And you'll get a finer curve. So that's kind of neat. I thought you ought to see that, but that's the technique that we're going to use a little bit today to draw our two favorite potentials, the oscillator and the Coulomb. Okay, now let's just take a look at some of the things that come from a zigzag. In this case, I have a zigzag associated with 2. It jumps up pretty fast, doubling each time, or halving each time. There's a zigzag right there, and I've just extended it so that you could make a sort of an architectural perspective drawing of some kind. You can see that it looks like it has some depth to it, you see. This is perspective geometry, where I've picked 2 as my ratio to characterize. Over here I picked s equal to half. Okay, sort of the inverse of that drawing is here. Okay, and it continues on down. I've gone ahead and drawn a few curves here for the inverse ones, using the lines that are projected off of the points that we find on the zigzag. Make another zigzag going this way. Okay, so you have 2 zigzags whose main lines are orthogonal to each other. You know that inverse is something, minus the inverse of a slope is a line that's perpendicular to the original. line. So that is a little bit of analytical geometry that you probably already have well established. But here we can see it in a rather clear way. And I like to say, if we want to relate this to our processes of education in this country, where we go to very nicely constructed schools, this is your perspective as a first grader on the first day of school. You're very short, and there are these huge, tall things. Your number is very big. As you get to be later on, first day of school for a 12th grader, okay, now you're tall, okay, and the hallways look like that. You're closer to the ceiling. Two different perspectives of the same hallway. Okay, so that'd be an amusing little sort of a one-dimensional perspective. Okay, there are kinds of things you can do with that, but we're going to go on to the physics. Here's a zigzag construction for just y equal x squared. It's found essentially by one zigzag for each point. Here you're asking, pick an x equal something line. Where's the parabola on that, associated with that point, okay? You zig from y equal x. That's the intersection point for what you've chosen. Zig to 1, okay? And then draw a line through from the origin where it intersects the 1. Bingo. We've got a point on the parabola that goes for this particular value of x. This particular zag line here, y equal question mark times x, hits this line at question mark times question mark, that's question mark squared. So I've faintly drawn a little parabola through that. Here's a better picture of that. Okay? And so forth. The idea is that you work off of the unit line, just a straight line using the 45 degree to locate you. So it's just taking the algebra apart and making it geometrical so that you can see the idea. Now when you zag to this line, you're going to get a point inside there on the parabola. Here you zag and you get a point outside at the intersection. Okay? It's this kind of construction that we'll use on the Coulomb, where we have an inverse power, but in any power law could be treated in a way that uses this kind of construction. This is a little bit simpler than the exponential one. Now there's some other pieces of geometry that I want to make sure you see. First of all, if we're going to be talking about an oscillator potential, a parabola, a u of x equal just x squared for now, then this little thing that we did before, where we make use of the fact that the force vector has to be equal to the derivative of the potential with respect to x, that is delta u over delta x of a triangle delta x and delta u whose hypotenuse is tangent to the curve. That's so that we don't have to talk about infinitesimal deltas as long as we keep the thing tangent and oriented and proportioned as the same as the triangle that would be an infinitesimal inside that by those pixels there. This is a good construction. So basically that's what I'm doing here. And of course this always turns out to be a normal to the tangent of this line right here. So this is just a picture of this thing done for these particular values of the potential at various values of the coordinate. And you can see that in this particular case, the force vector is just the length to the center line. that is going up linearly. What's not linear, of course, is separation of them. But that's the idea. This is a Hooke law of force that's being represented on the potential. So that's just another little piece of geometry that lets you see the parabola from another point of view than you're maybe used to. Now you're probably more used to conventional parabolic geometry that uses a focal point. And we'll tackle that one too. When we get this graph going on the board here, we'll look at the inside Earth potential, but first I have to explain to you why that potential is oscillator potential inside. But in any case, the idea is that, and this comes from optics most easily, that if rays of light are coming down the axis of a parabola, and this is a reflecting surface right here, then they will reflect off the parabola with angle of incidence to the tangent equal to angle of reflection to the tangent, and head right to going through the focal point. So what we need to do is review our focal point geometry. This is blown up a little bit there, but I've got a lot more to say about it than this. This is a standard presentation of parabolic geometrical optics. A vertical incoming ray reflects to the focus no matter where it comes, as long as it's vertical. And vice versa, if this is a light bulb on a filament, light source, diode now, at the center of your headlights, then all of the rays that are going from there, no matter whether you go down here or over here or here, go straight up this axis. To the degree of approximation, the light can be treated using a ray approximation. And this is a very good case of that. So there are a couple of geometrical things that we need to name that come up here. One thing that I will be pointing out to you in great detail is these little arcs right here. If I come down a distance below the lowest point of the parabola equal to the focal distance, I get something that we call the directrix. And this distance from the focus to the directrix is a very important quantity. It's called in the old books lattice rectum, but that has somewhat of an anal connotation. So I'm going to, clean up this act a little bit here, and just replace that rectum with radius. It is a radius of a parabola, a lattice radius is what we'll call it. And I'm doing this for legal reasons as well. The old term lattice rectum is now exclusively copyrighted by the Extreme Roid Ray Gyms at Venice Beach, California, zip code 9017. So stay away from it. It's only going to make your students giggle. So let's use lattice radius for this distance right here. And that distance will be equal to this distance. That is, half the lattice radius is the distance to the lowest point of the parabola, the extremum of the parabola, the point where it intersects its symmetry axis, the symmetry point we might call that. So these are 2 lambda over 2 equal to lambda. Now there's something else that I need to point out, is that if you're going to use the optical analog, and these are things you also check with calculus, but you should note that if I go straight out horizontally, perpendicular to the parabola's axis, then I must reflect from this point into the beam. Okay? So that means that no matter what the parabola is, whatever constants it has, whatever shape it has, opposite its focus is a slope of unity. A 45-degree slope has to be there in order to echo the light straight up from straight horizontal. To reflect from a horizontal beam to a vertical beam requires, at that very point, a 45-degree slope, unit slope, okay? In other words, a line that goes right through there, okay? The intersection of the directrix with the main axis. It's that idea that I want to elaborate on, because that is a much more powerful way to deal with the parabola. But let's look at any arbitrary point, and we're going to be able to make a definition here about the directrix, and that is the distance to the focus is equal to the distance to the directrix. And I mean perpendicular distance. You're talking about a point distance from a line you measure along perpendicular. So if you strike an arc from that focus, it's going to be tangent to the directrix at this point. And the figure that you make by doing that, and the other thing that's interesting is to draw a tangent. It will bisect that thing and make what we call the axis of a kite, a parabolic kite, which is coming next. So far, so good. Are these things that you can relate to? Sort of. These are things that you definitely want to get into your head. There are all sorts of places where you'll be ahead, particularly in this course, but anywhere that works with these kinds of
just
things.
1 second. So you said that something makes 45 degrees. So which means the tangent to the parabola at the point.
Well, let's take this point, for example, right
Yeah.
here. Okay? That would be pretty close to a tangent, right?
Right.
And that line would run right down here and bisect this. It has to do that in order that the incident angle be equal to the reflected angle. That help? Now, when you roll your tangent down to here, you see, a light beam coming down and reflecting off of the ruler right there has to go to the focus, as they all do. But now, this has to have a slope unit. And then it gets right, but the same thing is going to happen, you see. Every time I draw this, I'm going to get a figure that I call a kite, but it's going to look like a Chinese kite as opposed to an American kite. But it's still a useful thing. And where that touches, there's a line going through that that's useful for the geometry. But this is just a start. This is something that, this geometry should be known by everyone. What we're going to show you next is a little extra. Okay, let's move to a little extra. Basically the same figure, except now I'm drawing the whole kite. That's really, I think, beautiful. This is an American kite, right? It has an axis with two triangles, one big triangle, and then usually a little piece of wood or string going across that way, and then a point right here for two equal triangles. So this is an isosceles triangle here, and here's another one. Okay? Now if you go to the case where the angle is 45 degrees, the kite turns into a square. Then when you go inside, it turns into a rhombus. So this is what I really want you to get into your repertoire, is the ability to analyze equations like this. And this is standard notation right here. This is not so standard, but it should be. the idea of 4 times the focal distance. P is the lattice radius over 2. Lambda over 2. Okay? And then here's lambda, which is twice that coefficient, P, in the usual equation for a parabola, 4Py equals x squared. It's 2 lambda times y is better than 4P times y, I think, for what we're going to be doing, because it then there will correspond. You see, the lambda later on, fortunately named with a Greek L, is the thing that's determined by angular momentum. That's pretty cool. In the Coulomb orbits, okay? A little different in the oscillator orbits, but oscillator orbits aren't so concerned with where the focus is. They're concerned with the rectilinear properties of the parabola, the xy properties. This is more like a discussion of the polar representation of a conic section, in this case a parabola. And it generalizes to the other ones much better than the Cartesian one does. All right. Well, let's do the dirty deed that we have to do, and that is to construct on graph paper a few points for both the force curve and the potential curve for the outside of the Earth. And then we'll come back and look maybe a little bit more at the inside elliptical thing. So what we're talking about here is an Earth that has a radius of 1. We're being geometrical here, so we're scaling everything so that this is right here is our unit that we work with. And what I'd like to do is take the force curves and the various other parts of this thing right up to the surface of the Earth. That's our right here. Symbol for the Earth is a circle with a plus sign inside it representing longitude and latitude, I guess, as opposed to this symbol that we'll see later, which is a symbol for the radius of the sun. So what I'm going to do is play a zigzag off of that unit line. For instance, if I want to know what is the potential 1 over x, and this is x, and this is going to be a plot of u of x with potential being on the x-axis. And at the same time, we're going to superimpose on that plot the curve associated with, I should say, and, or, depends on which scale you look at, and or the force function, F. Now, you could easily say, well, I already know what that is. The force function minus 1 over x squared is what we're plotting. And the potential function 1 over x, also with a minus sign, is the other curve that we're going to be plotting. Just on seeing them on top of each other, see which one gets bigger, quicker, and all of that sort of thing. So, for example, if I wanted to find the point associated with x equal 2, the prescription that I have outlined here, based on similar triangles, which is down here in the right-hand corner, but here it is actually being worked out with a point x equal 2, which is what we're going to do first. So I'm going to be drawing a zigzag to the center there's the zig, and there's the zag right there. So I'm going to go and point at the center until I get to the 1, and then I'm going to stop right there, and that's going to be my value for 1 over x. And while I'm at it, I can go ahead and draw a zig to the origin again and get 1 over x squared. Now these are with minus signs, all below 0. So that's where the curves are all going to lie, is below what we call the escape point, escape energy actually, if you're talking about the potential. Now, let's see if everything is the same here as I'm about to do here. And it's much harder to do it on the board than it will be on your graph. But set yourself up with a graph that has, probably set the graph paper horizontally so you have more distance this way than you do this way. And use the unit of a half as an inch, so you should have from the beginning of the graph, which would be here, that would be -2. That would be an inch. I'm sorry, that would be an inch, and there would be 2 inches. That would be 3 inches, that would be 4 inches, that would be 5 inches, and then there's 6 inches. So it gives you plenty of room on an 8-inch wide graph paper turned horizontally. And then you need at least on the right-hand side 6 inches. That's twice 3 out. And that if you're talking about 10 inches, then you have 4 inches, plenty of room on this side. We're not going to go any more past 2 inches from the main axis of the graph. So the first part of your construction that we want to do is we want to know where is the value of the potential 1 over 2. Well, it's a quarter, but let's pretend we don't know that. So I've got to go down here to the unit, in this case the minus unit, and I start my ruler pointing at the origin, like that. And then just to show me what I've done, I draw a little sort of dashed line along that. I've already got little bits of it there. And it helps maybe just to draw a construction line just very faintly up to the origin so you know which one you've done, because it points back to the intersection of the 1 with the coordinate that you're interested in, which is in this case x equal 2. But once you've got here, you've got the answer, but you need to put the answer in the right place. So that's the zig. Then the zag comes back from that point along this line to the original coordinate that you chose for the first point. Okay? So the first point for this potential, okay, is going to be right here. And I've drawn that up here as a little circle. Okay? So I'll do the same here. I'll just put a little circle at that point. Okay, now once you've gotten that thing, there's nothing to stop you from going ahead and drawing another zig from that coordinate point now through this and seeing where it intersects the unit, and that will be your 1 over x squared. So I go ahead and I'm just putting the ruler down to do that, just to indicate the process, and I stop, and there's the value that I'm interested in. And you see you have graph paper to help you find where that point, that's the zig, here's the zag comes back to this point. And I draw another point. This one, in a graph here, I circle with a little diamond. So that's the idea of this. For example, let's stop for just a moment and make sure that everyone is following this, and then we'll go and get a couple more points for this graph. And the next slide here shows what we should be constructing after we've done this a dozen or so times. It's a very simple triangular, similar triangular geometry that lets us make these things very quickly. Now, what I won't bother showing you the details of is that this procedure can be carried inside the x = 1 to give you a Coulomb force and potential that are headed toward -infinity, both of them, one of them more rapidly than the other. And the one that's headed toward the axis most quickly here is the one that's the slowest to approach the x-axis, namely the 1/x is a quantity that takes a long time to get to small values, whereas the force drops off very rapidly. Force is what we feel. Potential we do not feel directly, unless you're a fancy oscillator of some kind. And general relativity is making you wiggle according to your potential. But as far as actually feeling a force, the green is what we're interested in. That's what's making you go. The potential is just the potential to go. So, let's say we want to do 1.5, or some point in between. Any point in between there, you do the same trick. I'll just take 1.5. Now using red chalks to indicate that I'm about to draw a potential, and I will head for the origin, to zig. I'll zig to the unit here, and I wind up there. This time I might not be landing on part of the graph that is lines on it, and certainly not this coarse graph. And then I come back, you see, and I have to make sure I come back to where I want to be. Graph paper helps you do that precisely, but I'll just trace the construction line. So there, right there, will be another point on the Coulomb potential. Okay? And you can see it's a little bit lower, quite a bit lower, than the other one. So there are a whole bunch of points in between there, which you get by taking, say, this coordinate, this coordinate, this coordinate, this coordinate, this coordinate, and so forth. Okay? But once you've got that, you might as well put your ruler toward the origin, do the zig for the force function, 1/x². Okay? So I do that, and I draw a line from that point up to the unit, which gives me the actual value of the force, but I need to zag that back to the coordinate that is assigned that value. By drawing a horizontal line in the graphic will help me do that. This one has come down a lot more. It's right here, so this is the next diamond that we've drawn, second diamond, on the force curve. Force curve goes through those 2 points. Potential curve goes through those 2, and so forth. Okay? So this is one of your exercises. It's a big problem. I want you to go ahead and finish this graph, even a little bit down here. Figure out how you do the points down here, where the force overlaps, actually intersects the potential at x = 1 and energy or force equal to -1. Now, at this particular point is the surface of what we're going to call the Earth. Now, where you draw the Earth, I could just draw it where you would think you would draw a circle that goes right through, or uses a center of origin and intersects what I've called the radius of the gravitational body. So the curves that we're constructing here are going to terminate, and I might as well just go ahead and put a circular dot and a diamond dot right on top of that point. That's a point right there where this stops being a Coulomb force and switches just 100% from Coulomb to the Hooke's law, linear force or quadratic potential. This is an inverse quadratic force. An inverse linear potential is kind of switches on the inside. I'll very lightly sketch what the force curve will be, and it will be coming down here and having approximately a slope of 2, exactly a slope of 2 at that point. And then the Coulomb potential will be coming along here just sort of lazily and waiting at pretty close to the last minute to come over here and cut through there, almost unit slope in this region, but exactly unit slope at that point, and that's where we start the parabola. Now, I'm going to talk a little bit about the units, but let's just pause to make sure that you clear on the geometry of the outside. You should be able now to make curves that go up, getting closer and closer to this axis, force getting close very, very much more rapidly than the potential. And they're together here, and now they're going to change radically. I can tell you what the force is going to be very easily. Force is linear. If the force is that right there and it's 0 at the origin and it's linear, I know that the force curve is going to be this thing. And I'll use a sort of greenish chalk to match what's on the screen to draw that. So here's the force curve inside. That's really simple. Inside the Earth, this is what we deal with. Now we have to justify this with some more geometry, but you know it so well from what you've done in earlier classes that I shouldn't have to stop and do that first, but we'll take that on in just a minute. Meanwhile, outside, and of course, if this is a uniform sophomore physics Earth, these are exact expressions for force and potential. If it's a uniform charge sphere, it's also applicable. But the constants are really different. First of all, the electrostatic constant is so enormous. It's 1 over 4 pi epsilon 0 in MKS units. 9 billion, or roughly. Roughly. It's actually 8.987 if I find one. Don't trust anything beyond there necessarily. We have units problems with electrostatic constant. One of our most well metrologized constants. It's certainly a very important one. So 9E9 is a good way to remember. Or it's very close to 10 to the 10th. If you want to be really rough, this constant is 10 to the 10th. But I like to remember 989. I'm not a good memory, so I don't remember these numbers. But there's another unit that you need to make use of this for most of the applications of classical mechanics, atomic and molecular theory, and that's the electronic charge, which is really tiny. But you have to realize that if you do have a coulomb, a unit of charge, you've got a real problem. It's gigantic. At 1 meter, it's got this enormous force and energy, as we'll see. Now you might say, well, then the coulomb's a lousy unit. Shouldn't use it in a unit that makes me have such a huge force for just one of them. But remember that 1 ampere is a coulomb per second. So every time you turn on a flashlight, you're putting a coulomb per second through a filament of an old-fashioned flashlight. We don't have that much going now. We can use milliamperes to get a good light with our diodes, thanks to quantum physics. But to the old-fashioned light bulbs, an amp is a small amount of current for a bright bulb. Okay? So, in that sense, coulomb's what we ordered. The doctor ordered for a good unit. When you come down to electrostatics, whoa, it's huge. And this point needs to be made more. This is something Feynman is good at, is describing the sizes of things. The other thing that's interesting is that the force can be plus or minus. It's repulsive if it's a plus on a plus or a minus on a minus. It's attractive if they're opposite. The old opposites attract maximum for marriage of humans sort of is in the right sign anyway for charge. Now I'd like to begin my fingertip physics, as I call it. We're going to talk about things that are only as big as about a centimeter. It's, you know, that's pretty good measure of your, just the first joint of your finger. This is, for mine, it's very close on the pinky. So let's see what we got in a pinky. Okay, roughly 1 gram of water, because that's mostly what we're made of. Okay, 1 gram of water is 1/18 of a mole. Mole has 6 times 10 to the 23rd Avogadro number of molecules. Okay, and we're talking about 1/18 of that. So we got about 0.3, a third of 10 to the 23rd. This is H2O that we're looking at the moment for the things that are mostly makes up my pinky here. Okay, talking about 10 electrons and 10 protons. So this 0.3 becomes 3. So we're talking about what we really have are 3 times 10 to the 23rd protons, hopefully pretty well counterbalanced with 3 times 10 to the 23rd electrons, all doing different jobs to hold the pinky together, which is an amazing bit of physics. Okay? And that is 3 times 10 to the 23 times 1.6 10 to the minus 19th coulombs. So that cuts it down, but it's still enormous. Remember, coulomb does this, okay? 1 coulomb. We've got 50,000 coulombs in your pinky. And most other matter, right? This is the order of magnitude that you're talking about. Just sitting there. If we got rid of one of these others, there'd be an explosion, a very serious explosion. You would essentially wipe out Fayetteville with your pinky. As I say in the text, does your manicurist know about this? Hopefully they wouldn't refuse your services. because of that. So you got to realize when you think about the numbers that are associated with these force laws, that they are really quite astronomical. Now, here we have a possibility of being repulsive and attractive versus, and this is, I think, a great mystery, but always attractive gravitational Coulomb, where our units are now going to be kilograms in MKS, kg, and same force units, newtons, same distance units, meters.
Dr. Harter, do we understand why force of gravity is much weaker than electrosonic?
boy.
I mean, why is there?
I would say absolutely not. But there are people in string theory who say, hey, I think if we took two brains and put it with a string and something else, and you know, when abracadabra, I can get you within 10 orders of magnitude of this ratio. I don't believe a word they're saying, because nothing else they can deal with even comes that close to working. So the answer is absolutely not. Big mystery. Now what we're hoping is it's a wave trick. If we can really understand our relativistic nature of the Coulomb, and then see what it is when you realize that the Planck's law is telling you that energy is nothing but wrinkles per time, momentum is nothing but wrinkles per space, right? So we're talking about wrinkles that curve something, a gauge if you like. You can give them funny names for things you don't understand, right? But if you have a tremendous amount of wrinkles, which you would have to have in order to have energy associated with the relativistic MC
So
squared.
wrinkles, you mean movement of propagation of waves?
Yes, the waves that make the thing up are very wrinkly when their energy is high. And rest energy is enormous, huge for even electron. Okay, you're talking about frequencies of hertz. So it's very wrinkly, and you put a whole bunch of them together, make a whole planet or something. You got wrinkles. It's just a wrinkle fest below your feet here. Now, how do those wrinkles make a very gentle wrinkle in the space of time? Something is not quite adding up, and that's called gravity. So you've got to figure out how the wrinkles make an extra wrinkle that we call curvature of
When you say wrinkle
space-time.
physically, what is it? Wrinkle of what? Like, is it of space-time, the very space-time?
That is what general relativity would have you believe, is that you can explain the gravitational forces precisely by knowing what the curvature of the space is. And the curvature of space is measured by what's called the Ricci tensor, and that tensor is proportional to the stress energy tensor. Why? We just did it because the symmetry matches. But we don't know. That doesn't explain how, we get these two different things. I have to put that constant into the stress energy tensor.
I have two more questions. Like, do we understand why we have got two kinds of charges? Just positive. Can we explain that one? Like,
Once again, it's one of those things that becomes an axiom, but I would say it has to do, that is, when you finally get an electron that's obeying this dispersion function, and one that's obeying this one, which you call positron, that you get an orbit. And that orbit has a certain frequency, and that frequency is very close to 2mc squared, which is the separation between those. That's the gap. So we have a little better of a feeling for that than we do to your first question.
no, like, once again, like, what is the answer? Like, why we have got two kinds of charges, like positive and negative?
What does that mean? We don't know.
Oh, okay.
We really don't. We need to find out. It's been a long time since we've been using these things, and they work very well for us. We know enough to do a lot of engineering with it, right? Sitting here with all of this wonderful projecting equipment and computers and, you know, got the room heated or air conditioned. I mean, everything's working. Doesn't mean we understand it, right? At the at the lowest level. We get used to this stuff, right? And we don't ask those questions, but those are good questions. Just bother you every night, right? I don't want you to be neurotic about them, but I want you to treat them with respect and keep them in mind. So, let's go ahead here and look a little bit at the energy, the electrostatic force we just discussed. This is the energy curve that we've been plotting on the board. 1 over r instead of 1 over r squared, where the 1 is this 9E9 giant times however many coulombs you're talking about for the source, the big Q, and the little thing that's going to be orbiting in an atom, for example, a little q. They're both the same if you're talking about positronium. Let's get some ideas about the size of things that are involved with building charged matter, atoms in particular. The typical atomic size, as you know, is an angstrom. That's 10 to the minus 10 meters. That's a tenth of a nanometer, but the diameter is what I'm referring to here. Actually, the hydrogen atom is very close to the Bohr radius of 1/2 of an angstrom. So that means the Bohr diameter is very roughly an angstrom. That's 10 to the minus 1, 1/10 of the favorite unit, nanometer, right? We talk about it around here so much because we're making things that are roughly on the size of a few nanometers. So it's a few atoms that you're talking about when you say a few nanometers. But inside each of those atoms is a tiny, 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 tiny dot. Typical nuclear size is 100,000 times smaller, 10 to the minus 15. That's a femtometer, I guess we could pronounce it. It's a unit that is very scary. And you see, whereas a big molecule would typically be close to 10 angstroms, like buckyball, even that's not quite that big. There you're talking about a full nanometer. A molecule would be taking up a diameter of close to a nanometer, nanometer. This unit, 1 FM, and this is one of the few units that you can either write it lowercase fm or uppercase fm. Lowercase goes with the femto, but the uppercase goes with Enrico Fermi, one of the greatest theorists and experimental physicists ever. It's the person that did the beginnings of nuclear physics at the 1930s and 40s, and you know where that led to. We'll talk a little bit about the nuclear fission energy, but you have to be aware that 1 Fermi, or 1 femtometer, 10 to the minus 13 centimeter, 10 to the minus 15 meters, 1 femtometer, I'm not drawing it to scale here at all, right? I'd have to make a fraction of a pixel with an electronic orbital of that size. It's just a speck. Tiny, tiny, tiny. That is, you know, if you want to ask a question, why is that? Well, we don't know that either. Okay? It just is. And we've done scattering experiments, which we'll talk about later in this class. Okay? So what I'm saying is that nuclear radii are 100,000 to 1,000,000 times smaller than the typical atomic/chemical radii. So that means that nuclear Q over R energy is proportionally, because of the proportional effect of 1 over R, is proportionally that many times bigger, because this is inverse R, than the atomic or chemical energy that we gain from electrostatic forces.
Oh, because of the one over R dependency.
Yes, yes. So if you're worried about the your pinky blowing up because there's a charge that's separated by a centimeter, you should worry even more because for the atoms it's separated by only a few nanometers, but for the nuclei it's separated by femtometers. And this is the formula, once you know this constant, that you use to figure out how much energy you're going to get from a chemical explosion where the electrons suddenly become non-bonding.
But this nuclear energy that you're talking about, Dr. Harter, is only due to the repulsion between protons, right? This
Right.
You don't take the energy of neutrons into account in this.
You don't need to.
Okay.
It is very small effect.
Ah, okay.
Once a uranium-235 nucleus starts to do the very large oscillations that we think the liquid drop model should tell us, and forms of two droplets, now you really have two things with roughly 40 or 50 coulombs, these, I should say charge units, separated by just a fraction of a femtometer. Whereas in a chemical explosion like trinitrotoluene, you have two aniline groups that separate with only a nanometer separating them. Roughly the same amount of charge. So this is the factor that determines the ratio, roughly 100,000 to a million, between the energy you get from a typical kilogram of high explosives and a kilogram of either plutonium or uranium nuclear explosions. Okay? The kind of stuff that Sterling Colgate was so fascinated with. And of course he helped take it to the next step where he worked with something where you get even more energy from the fusion of the tritium and deuterium in what's called the hydrogen thermonuclear device. I mean, they use all kinds of euphemistic terminologies for what is a terrible bomb. Terrible, terrible bomb. But then the number is yet another 1,000 or so. And that's even more of a mystery. But this one is just Coulomb. The atomic bomb is just Coulomb. Okay. Well, let's go back to the Earth. We've got about 10 minutes here, 10 or 15, depending on how we measure our starting point. This is something that you should already have committed to your lore of knowledge, and that is that if you have a spherical shell, uniform density, the gravitational, or if it's electrostatic, the shell of charge, vanishes inside the shell. So this is a Gauss law sort of truth, but you should see why, in geometrical terms, the Gauss law applies. What you're really looking at is the gravitational potential at an R, some radius R, say that point right there, due to incremental pieces of the shell, which you would produce by extending a solid angle from that point to the shell, and then summing all of those solid angles by means of a calculus. That's something that you've probably already done as an exercise. But the geometry of the thing is rather telling in the sense that it will tell you right away that the total of this has to be 0. Because the amount of charge that you're seeing inside your little cone there is proportional to d squared. But then the energy associated with that, these I should say the force associated with that is inversely proportional to that d squared. So when you look at the one on this side and the one on that side, even for just these two, the force cancels. For everything that's pulling you along one of the lines in that cone, there's an equal number of things pulling with equally in the opposite direction. So cancellation is simply a geometrical fact. And then you rotate to some other solid and some other, all cancel, nothing is achieved, and you are weightless if this was mass. And you're force-free if you're a little charge inside a spherical charge. Okay, so that's really quite, I think, remarkable. Now, at this point, I'd like to have your imagination stimulated, so I imagine, suppose that we were standing right now in this room on a shell the size of the Earth, with all of the mass just compressed to, you know, a foot or a few inches, shell, thickness of a shell. And I pull back the rug and there's a manhole cover, okay, which with appropriate equipment I can, it's pretty massive, but I've got the equipment to open the shell, slide the manhole cover over so that we can, ooh, look, it's sort of a dark hole in there, isn't it, okay? And then we imagine that we're daredevils, right? So I want to see how much I weigh in the hole, you see. So I get down and I stick my feet in the hole and I start laying myself down. I let myself down, okay? Now I'm sort of looking at you along the floor, I'm looking at your feet, right? Okay? But I don't weigh very much now. And finally I go until the top of my head is just below the center of that shell. I can let go there. And I won't move. I'm completely free of gravity. I'm just floating there. Now, the mistake would be to let go here, or worse here, right? I let go and I fall. Oh, whoa! Well, now what are we going to do? I'm just going to drift all the way through to Australia on the other side. Maybe there's a manhole there will let me out. Probably not, because everything rotated. There's all kinds of problems if I let that happen. Anyway, this is these kind of fairy stories that we like to tell.
So which means
They give you some feeling for what the physics you're doing really means.
yeah, there is no field inside a spherical shell.
No force.
So no, which means no,
Lots of potential. Wherever it's stopped, it's going to be constant potential in there.
yeah, which means there's no field, so there is no force. So if we construct a spherical shell, a hollow spherical shell where
Right.
the mass is just on the edges, like on the
Uniform.
surface of the shell,
It has to be uniform.
uniform mass distribution. And if I stand inside the shell, so will I experience weightlessness?
If that was the only mass around, now we're talking about the whole Earth here,
Okay.
right?
Okay.
Now what's going to happen is I get in there, right? Now I'm going to start to feel the moon. Won't be a big thing, but it's going. I'm going to be a tide. I'm a part of a tide, right? So that's an interesting aside to this. Now, what I need this for is to say that the Coulomb force inside a spherical body is due to the stuff, the mass, below where you are located. So you're located here at R little or lesser, okay? And any mass that's in the gray here has no effect on you. If I were to take all the mass out of here, I'd have a shell. So it doesn't matter how thick the shell is, as long as you're inside it, you're force-free. So all the force that I feel here will be due to this. Right? So the force at an inside radius, and that's what we're after here, is the force inside the Earth, of the sophomore Earth, sophomore physics Earth, okay, is whatever mass is below me, m lesser, and the radius that's below me, r lesser, squared. That is the force right there. So I'm going to turn it into, I'm going to multiply and divide by r here, so that I get a 4 pi 3 r cubed. That's a volume, okay, which I can take out of the mass and call it a density. And then I've got this thirds pi gm to worry about this. Remember, this is the whole volume right here, and that's the mass. The mass per volume gives me a rho of Earth, okay, times 4/3 pi, and gm, and g is this really tiny constant, which, by the way, I'm going to jump back here real quick, but I forgot to point out something, I think, about this. Oh my gosh, I guess I just left it out, but the ratio of these constants, just look at this. This one is 10 to the 10th. This one is 2/3 times 10 to the minus 10th. Okay? So we're talking about 10 to the 20th in MKS units, meter, kilogram, seconds. I forgot about that, so be sure and remember that. In any case, that's what we're dealing with here. And you can see what's happened is the little radius divided by the radius of the Earth, that's mgr, because mg is what you've got at the surface, and this thing's going to be, this is the force that you would have on the thing. And this is what x is. X here is a scaled quantity involving the radius of the Earth. It's 1 when you get to the surface, it's less than 1 when you go inside. So Earth's surface gravity acceleration, right? It's whatever acceleration you get when this thing is equal to the radius of the Earth. That's it, right there. Took one of the masses off. The test mass, you might call it. Okay? So I can multiply this thing by r0, that's r cubed. You do the same trick, 4 pi over 3 divided by 4 pi over 3, okay? Then I get an expression for g, 4 pi over 3, density, radius of the Earth, having replaced this little r little here with the radius of the Earth. That's our connection, you see, with what you know, 9.8 meters per second. So there's your connection with the units of force or acceleration that we have up there. To give you an idea for other bodies, first of all, Earth radius. That's pretty easy to remember. I've been able to remember that pretty well. 6 times 10 to the 6, but it's actually 6.4 times 10 to the 6. Okay, that's divisible by 4, so I can remember that. That's kind of a nice thing. It's 6.371 times 10 to the 6. That's the answer. Earth mass is almost 6 times 10 to the 24th. Very close. That's really easy to remember, right? And it's solar's not bad either. It's 7 times 10 to the 8th. Okay, 7, 8. Or sequential. 10 to the 30 kilograms, it's twice that. Really close. So these are all numbers that we'll work with in the course. And most of the time when I'm just doing a rough calculation, I'll use these mnemonics. Another fortunate one is speed of light. It's 3. 29979, that's 3 for 4 figures. So, you know, a lot of nice coincidence in the MKS system. All right. Now, we're just about at the end of this, so I've got to, 5 more minutes now. I want to point out that we came up to the surface of the Earth with a slope of 1 there on this grid curve, which is the potential curve, the 1 over x curve. This has a slope of unity right here. So that tells you where the focus is of the parabola that's going to be the potential inside. Now here's where you use the kite construction to build. There's a typical kite making a bisecting tangent. You just take a rectangle and slide its corner along the directrix down here, and you can very quickly fare out a parabola. But knowing the focus, you can do it too, because you know that there's the focus, therefore the directrix has to be right there. So this is, you know, the sketch of the construction which I want you to do inside the Earth as well. And then you should be able to extend that. This is the construction I was talking about, the kites making their tangents and the relationship to the focus and the directrix. They point at a halfway point for the kite, and they indicate on this intersection what particular value of the slope you're dealing with at that particular point. So there's a lot of things that you should know. The tangent slope there is -5/2. The slope there is 1/2. It's just rooted off in units of p on the half directory. So we would call the umbilical point of the curve. Anyway, that's really what it is. Now, you crush the Earth. This is something we're going to do in a minute here, but I wanted to point out also that there are 3 energy levels that are of interest here. If we're going to have this neutron starlet orbiting about using the Coulomb potential or force outside of the Earth, it could very easily be knocked so that every once in a while it would come through the Earth, and then it would be making as we'll show, an elliptical orbit inside the Earth. It's important to see where are the interesting points associated with this. And if you're thinking like a quantum mechanic, you're thinking about energy levels. And where's the lowest energy that you could have for that neutron starlet? And that would be to be stationary at the center of the Earth, and would have to be here at the bottom of the parabolic well. Okay? Now, if you can drag that neutron starlet up a tunnel so that it comes up to the surface of the Earth, that is, you drag it along a tunnel to this point, then its potential right here, that's the surface level potential. That's just minus g mass of Earth over the radius of the Earth. The thing to notice is that this ground level potential in those same units is -3/2. So it's going to be right here. Your parabola is going to come out and go right into that, right there. So there's your lowest point, -1.5 in our geometrical units. But if you drag me up to here, you give me a half unit of energy, I can sit on the surface of the Earth. Give me another half and I can do something cool. I can get into a circular orbit. That's the next step right here, orbital level. Okay, energy level. Circular orbit outside, just outside, or just inside, they're both the same, of the Earth. Okay, that's where the potential energy curves and the force curve and everything on our units intersect. Okay, so there's the thing. And then if you give me another half, I'm out of here. I can, neutron starlet can go back wherever the hell it came from, go to infinity, and have zero velocity at great distance. So those are the 3 steps that you want to look for in this little Disney-like physical model of the sophomore Earth. Crush it to half, you'll increase them by various factors. And this I'd like to have you study, but now the parabola is going to be a little deeper, and its focal point is going to be very close to the bottom. That's where I see unit slope way down there. Here I've got a huge slope. So just work the arithmetic through this. Crushed Earth, 1/2 radius, 8 times as dense, 1/8 of a focal distance, or 1/8 of a lattice radius. 1/8 of the minimum radius of curvature, which is now getting into the curvature that you would actually see in general relativity. 8 times maximum curvature. Okay? Those two are reciprocal of each other. So there's a, just to give you a feeling for what the sophomore physics Earth, if crushed, and there would again be 3 equal steps. Okay, let's go even further. we're going to take the crushed matter. That is, we're going to take the matter that we have for the sophomore physics Earth. You work it out by taking the 6 times 10 to the 24th kilograms and the Earth's volume, which is this 4/3 pi r cubed with a radius here of 6.4 million meters, 1,000 kilometers, okay? And put those together with to make the density. The density of the Earth is about 6,000 kilograms per cubic meter. Cubic meter is a lot of dirt. Okay, so we're talking about 6,000 kilograms, multiply that by 2.2, you're talking about several tons. Density of a solid iron is only a little bit larger, 8 or so, this. Density of liquid iron, a little less. Okay, these are things that you get out of Handbook of Chemistry and Physics. Again, a lot of physics behind that. But the iron core of the Earth is a major contributor to its mass, and that's what makes it not sophomore physics anymore. That's geology of very complex stuff. But the nuclear matter, let's take that. Okay, we're talking about a nucleon with 1.67 10 to the minus 7 kilograms. Let's call that 2 times 10 to the minus 27. Say the nucleus is atomic weight of 50 and a radius of 3 femtometers, a typical radius for a middle-aged atom, nucleus. Each has a mass of 2 times 10 to the 27 kilograms in a nucleon. Okay, so that comes out to about 10 to the minus 25th kilograms packed into a volume of 4/3 pi r cubed, where r is those femtometers, 3 femtometers. Well, that's 10 to the minus 43rd cubic meters, really tiny volume. Okay, and 36 pi is pretty close to 100. So we put that all together and we get a nuclear density of 10 to the 18th kilograms per cubic meter, or a trillion kilograms in your fingertip, 1 cc. Okay, so this is a neutron starlet. Now, if the Earth is crushed by a factor of 100,000, but just half of that, okay, to a radius of 300 meters, it would then have very close to neutron star density. So imagine 300, that's 600 meters in diameter. It's a little less than a kilometer in diameter. That's pretty tiny. Here's the Earth, you know, just a dot, right? I want to go one step further. How far would you have to crush it to make a black hole? Take a short shield, okay? So this right here is introducing a neutron starlet, trillion kilograms in your pinky. That's pretty dense, okay? And that thing is going to orbit forever. Its damping is essentially 0. It will orbit according to the rules of the sophomore Earth, pretty close, elliptical orbit. The black hole Earth, whole nother story. I want to crush it so that the surface escape velocity is the speed of light, which is 299 and 729, 458, but it's 310.8, okay? I want a velocity of escape of 310.8. This is the formula from page 43 of back yonder, okay? And then the gravitational constant has to be put in there too. 2/3 of 10 to the minus 10th, roughly, okay? Well, it comes out to about 8.9 millimeters, about a centimeter. So if you can crush the Earth to your pinky, you've got a black hole. That's the end of the fingertip physics. And next time we will be taking on orbits. Since we're running over just now a few minutes, I will just stop right there. But we're going to have fun with the neutron starlet in our imagination. Orbiting. How would you tell this is not happening? There's so much activity down there that just doing a very careful seismic analysis might not work. They could be down there, the neutron starlets, doing orbits. So, just, you know, the media likes to make you be afraid, be very afraid. That's the best I can do at this moment.